Okay, so hello everyone. So I'm Lise Ramambason. I'm a PhD student at CEA. And today my contribution in this workshop on uncertainties is specifically on topological models. So I will, of course, define what kind of models I'm talking about. And I will try to show you that they are a good way to account for specific problems when we try to model the ISM, especially one problem that was raised during the discussion by Jérôme, I think, when we have mixtures of components along a given line of sight, or when you try to model unresolved galaxies where you have only one pixel for your whole galaxy. But we will see also that it raises an additional layer of uncertainties. So this is a classical kind of model that I will call single component, in the sense that we consider only a single set of parameters. So here, I will take the example of photoionization models, although it could be any kind of model, where the parameters could be, for example, density, ionization parameters, stellar properties, or the metallicity. And the idea of topological models is to try to combine those models under different assumptions to represent the geometrical complexity which is hidden when you have only an unresolved view of a galaxy. So this can be done by different type of combination of models. The first one that I show is a multi-sector, where you assume, for example, that the emission that you are seeing is representing the contribution of different gas components with, for example, different densities. Another way of combining model is to assume a multi-cluster configuration where you consider that the emission is powered by different population of stars, for example, an old stellar cluster combined with a young stellar cluster. And the last one, probably the most interesting one, is assuming a distribution of parameters. So for example, here, the emissions that you're seeing arising from a galaxy is just the result of a combination of a population of H2 region or star forming region that you can describe with an analytical function. And for example, here I show a power law where you assume that your star forming region have a density or ionization power law distribution. All right. And with that kind of topological model, of course, you are doing a slightly better job than with single component models. And you can still predict emission lines that you want to compare to observation. So this is a very basic model, a very basic problem that you can find with any kind of model, even for non-topological ones, where you want to compare models with your observation, and you need some tools to do that. And I will add that you also want to account for possible upper limits when you have lines that are non-detected, possibly priors, systematic uncertainty when you have lines coming from different instruments or other kind of systematic uncertainty, and maybe asymmetric uncertainties. And for this, you need a statistical framework. So I will show you one tool that we developed during my PhD, which is doing all of this. And so this tool is called Multigris, and I will use it to exemplify as an example today. But it's doing a comparison very classical. So on the input, you have one model that you want to compare to some data. And the topological part is comes when you assume a given configuration. So you assume that you combine a given number of components or sectors. And the core of the code consists in sampling the likelihood. So for this, you can use, for example, Monte Carlo methods. And as an output, what you get are the probability distribution function, posterior probability distribution function of different parameters. And for example, here I show a corner plot, which is showing just 4 parameters in my model. So the stellar age, density, ionization parameter, and metallicity. For a 2-component model, that's why you have like 2 solutions on each plot. All right, so what is uncertain in this workflow? Well, basically everything. But we have already seen a lot of talks about the uncertainties associated with the models, the data. And I think one talk will also be talking about the uncertainty in the representation of the posterior PDFs. So I will just focus on those two uncertainty sources, the one coming from the topological configuration itself and the one coming from the sampling that we are using. So here is an example where we want to compare a model with a different number of sectors or components with either 1, 2, or 3 components. And we want to know which topological model should be favored by the knowledge that we have on a given set of lines. So one way to do this is to use the bias factor, which is just a relative metric where you compare the probability of a given model knowing the data to the probability of the second model knowing the data. And using the bias theorem, you can also express this as the ratio of the marginal likelihood times the prior probability of the models. Okay, so this is a nice metric, but you will see that it's not always easy to compute. So for example, I will start with the marginal likelihood, which is expressed by this equation where you integrate over the whole parameter space the likelihood of your data times the prior on the given parameter. So it's a very general problem for any Monte Carlo Walker. And one thing that a usual caveat is to make sure that you are not missing any solution. So for a Monte Carlo Walker, one classic problem is that it can get stuck in a local maxima, and that it might be missing some peaks in a multi-peak distribution. So on the little animation, what you can see is just a classical sampler called no U-turn, which is converging. So yeah, it's a temporal evolution, and you can see the convergence toward two solutions, because here it's the case with a two-component model with a nearest neighbor interpolation. That's why it's square solutions. However, as you can see on this animation, we are not sampling the whole parameter space. Some places are still blank. So the evaluation of the marginal likelihood is not super easy, because you cannot really just replace that integral by a sum. You really have to resort to integrated analytical function, which can be difficult. So I will now present another kind of method, which is called particle filtering method, which is a class of algorithm, which kind of provide an easy solution to evaluate this marginal likelihood. So the idea of this method is to simultaneously evaluate the whole parameter space by running parallel Monte Carlo chains. So as you can see on the animation this time, we start with a distribution which covers the whole parameter space right now. And then this distribution is being updated as the time progresses until it finally converges to the posterior PDFs of the parameters. And with that kind of sampler, it becomes very easy to evaluate the marginal likelihood, which is just a sum on all the dimensions that you assume. All right, and with the marginal likelihood, you can now, yes. So I put back the criterion that I was proposing to compare models. So you can now calculate the first terms, which is the ratio of the marginal likelihood. However, there is still a problem that you have to assume that the model have prior probability which are equal. So that brings me to my first question, which is it okay to assume so? Should we favor models which are more complex, that are more likely to represent the complexity of the ISM? And if so, how do we favor it? Should we put an arbitrary weight on such models? My second point is that with particle filtering method, it's well adapted to sample multi-peak distribution and to calculate the marginal likelihood. However, once we have this description of a multi-peak distribution, we still have the question of how do we represent it? Do we use a smooth distribution? How should we represent it for a whole sample? Can we stack PDF? Can we use smooth distribution for a whole sample of galaxies? And what happens when you have unpopulated bins in your galaxy sample? And my last point is that the posterior distribution that we get is reflecting the lines that we use and the associated uncertainties. So in my case, I assume them to be Gaussian. But two questions associated would be, what is the impact of the set of tracers that we use? Should we exclude some of them because we know that they are uncertain tracers, or we do not model them well in the model? Or should we take as many tracers as we can and just try to constrain the models with all that? And finally, my last question is, what is the impact of assuming fixed Gaussian uncertainties for the data? And ideally, one would like to redo the fitting process for each MCMC step, but of course, this is an expensive solution in terms of computation. So can we find another solution, a nice in-between to do this properly? And with this, I finish.